Hi, my name is Brionna Gibson. I'm going to be solving my combined spectral problem. I had group E. So my molecular formula that I was given is C4H6O2. So the first thing that I did is I went and solved for the degree of saturation. So I did the number of carbons, which is 4 times 2, gave me 8. I added 2 to that, and I got 10. So from that, you subtract the amount of hydrogens that you have, and that gave me 4. So 4 degrees of unsaturation, which is 2 pairs of hydrogens that are missing. That just tells you if you're going to have any double bonds or anything like that, which having 4 degrees of unsaturation meant that I should have 2 double bonds or a double bond and a ring. So I just kept that in mind as I was following through with the rest of it. So next I looked at the IR spectroscopy for the molecule. So at I always approach it by dividing up the graph. So I draw a line at 3,000 right there. I draw a line at 1,500. That's just because anything lower than 1,500 is the fingerprint, and it can be a little bit more difficult to determine what your molecule is by just looking at that. So I always start on this side of the graph. So the first thing that I always look at is anything greater than 3,000. Um, so I looked at this one and I saw this little spike right here, and I automatically thought that it was going to be a nitrogen hydrogen with 2 hydrogens since it has 2 little dips. I went through the entire rest of it, looked at the other 2 tables that were given, and then got to the end and I was trying to build my molecule, and I realized there were no nitrogen. So very important to always look at what you're given. So this right here really doesn't mean much to me, so I just kind of ignored that. This is also where I would find my oxygen and hydrogen bonds. So this would be a really wide and broad peak if there was an oxygen and hydrogen bond. So I just kind of ignored that for now. Then I looked right here at 3,000, and we have this little dip right after or right below 3,000 at like 2,900. This tells me that I have an sp3 carbon hydrogen bond. And then over here around 1790, I had a pretty large spike. So that told me that I had a carbon double bonded to an oxygen, which kind of tells me a carbonyl. Then from there, I can look at the under 1,500, and if I see anything that sticks out from the tables that I've been given and that I've looked at. So right here, at about 1150, there's this peak that's like that tells me there's a carbon and oxygen bond. So right here, thinking first degree. I mean, this was the first time I went through, so ignore that right there. But so from this, I'm definitely thinking that I'm having a carbonyl of some sort, a carbon and oxygen bond, and then right here, this sp3 carbon hydrogen. Then I looked at my carbon-13 NMR. So first, I always take a look at how many peaks there are. So there's 1, 2, 3, 4 peaks. That tells me that there are 4 unique carbons. There are 4 carbons in my molecule up here, so I know that each carbon is unique. So there's no symmetry in the in my molecule. So then I looked at my very first, my highest peak. Everything kind of from this point on is going to be more diagnostic for what you have. So right here at 180, this tells us that we're going to have a carbon double bonded to an oxygen that's also bonded to another electronegative atom. Specifically, oxygen for an ester is kind of the 180 is pretty diagnostic for an ester. So then I looked over here at the second peak. At 70, it indicates that there's a carbon bonded to an electronegative atom, which is carbon to oxygen, or it could be nitrogen. And that kind of matches up with the IR spectrum. So those are the two things. We have our carbonyl and we have a carbon oxygen that we found in our IR spectrum. So then these last two spikes down here, these are lower on the chart. So we have one at 20 and one at about like probably 30. These over here are sp3 carbons that are that don't have a dipole, so it would be your carbon to carbon or carbon to hydrogen bonds. So at this point, I knew I was looking at an ester because of the carbonyl and the carbon oxygen bond. So I drew that out, and then I just kind of went with, what I thought could possibly happen. I filled in the rest of it, the other carbons and the hydrogen. So with this one, I did have 4 carbons and 2 oxygens, but filling it out and following the octet rules and everything, I had 8 hydrogens, which does not fit my molecule. So I knew that wasn't correct. And then if I remembered back to my degrees of unsaturation, I remembered that I should have either 2 double bonds or a double bond in a ring. So then I was thinking, well, I need to see if I had a spike for carbon-carbon double bond. So if I look over here, this would be where we would see that at from 110 to 160, we would have a spike if we had a carbon to carbon double bond. So I pretty much knew at this point I was going to have a ring of some sort. So then I went over to our HNMR. I always count the amount of peaks that we have, which we had 1, 2, 3. So I wrote that out. That tells us that we'll have 3 sets of unique hydrogens. So then I started looking at each signal by itself. So the first one that I did in yellow, I first looked at the amount of spikes on this signal. It has 3 peaks, which tells me it's a triplet. The n+1 rule tells me that to get the amount of neighbors, I just need to subtract 1 from that. So I did 3 minus 1. It told me that I had 2 neighbors on that, or those hydrogens had 2 neighbors. Then I looked at the next one in pink. It also had 3 peaks, so the same thing. This one, the set of hydrogens only has 2 neighbors. Then I looked over here at the purple one. It has 5 peaks, so 1, 2, 3, 4, and 5. So that means it has 4 neighbors. So 5 minus 1 gives you 4. So from there, I looked at the actual ppm. So the yellow one is 4 to 4.5 over here somewhere. So with that means that it's going to be a hydrogen that's bonded to a carbon that's bonded to an electronegative atom. So we already know from the previous 2 charts that we have that we're going to have a carbon bonded to an oxygen for that part of our ester. So we know that this is probably going to be the set of hydrogens that's bonded to the carbon that's bonded to the oxygen. So I knew it wasn't the oxygen. This could also have meant that there's a oxygen-hydrogen bond, but I knew this wasn't true because of the IR spectrum. So then we look over here at the other 2 spikes, which are further right on the chart. So we have the pink one that has 2 neighbors. So this one is going to be where we have the carbon bonded to, or the carbonyl, so the carbon double bonded to the oxygen. This is going to be a hydrogen bonded to that. And then we have the 5 peak one, the lowest one. This is just going to be, just a normal hydrogen on carbons. So this one has 4 neighbors. So with all this information, I was able to start actually building my molecule. So first I wrote out the carbonyl. So I had a carbon double bonded to an oxygen. I knew it was an ester, so I did an oxygen bonded to that carbon. From here, I knew that it was going to be a ring, so I just filled that out with the correct amount of carbon. So I built the original, or the foundation for it. Then I just needed to add my H's. So I knew that I was going to have three unique sets. I knew from the HNMR how many hydrogens was in each unique set, which was two. So I had two hydrogens that were bonded to the carbon that's bonded to the oxygen. So that would be these two right here. And it has two neighbors, which is true because this one set of hydrogens has two neighbors right there. Then I went to down here. We've got the triplet that has two neighbors, and this one is a hydrogen bonded to a carbonyl. So this would be right here, these two hydrogens bonded to this carbonyl, and it also has two neighbors. Then lastly, I was able to pretty easily figure this part out. Four neighbors has to go in the middle. So this set of hydrogens has one, two, and then three, four neighbors. And that's how I was able to come up with my molecule. Here is my charts all filled out for a final molecule of this. And that sums it all up. And thank you so much.